Thank you for the kind introduction, and I'm really glad to be here today. Thank you for inviting me for this important event. I heard that this is the first meeting of the IEEE chapters, so congratulations of your new start. And actually, I'm the IEEE Sensors Council Distinguished Lecturer for 2025, the 2028. So this year is my first year to be the BRP here, and this is the very first lecture I ever deliver as a BL. So first meeting as a new chapter, first lecture as a BL, I think it's a good combination. Okay, so today I'm going to talk about the digital microfluidics for chemical sensing and biological sensing. Those who are not very familiar with where the Arlington is, we are located in the North Texas, Dallas-Fort Worth area, and we are the largest institute in the DFW area, and the second largest among the UT systems, and we are very active in the research. So from Hyejin, where I am and where I live, and then here is the Twin Cities. So it's about 2.5 hours of flight last night. And I'm really glad. This is my first time in Minnesota, so good experience. So brief introduction of my research. My lab is integrated micro and nanofluidic systems. So basically, I am not a sensor person per se. My background is more like microfluidics, handling the fluid in the very, very small scale, and then how we can utilize such a micro scale fluid in motion to build some useful devices. And then, as you can imagine, there's such a small scale fluidic handling techniques probably very beneficial for sensor development. So these are the some example of the research project that I previously did and currently doing. So today my talk is mostly focused on the Lebanon chip project. And then these are the red colored the projects are mostly closely related to the chemical biosensing, of course. So I'm going to talk about these projects. Okay, so my talk, I'm going to start with the electrowetting on dielectric, what it is, and then move to the example of the DIWA digital microfluidics that we developed in our lab. And then the part 3 is I think the most important part of this talk, because as a microfluidic person, I'm talking in front of the sensor researchers. So how can this conversation can make a benefit out of it? So I'd like to introduce what digital microfluidics is, and then sensor expert can think about how you can utilize or how you can help us to build more beneficial systems for the bio and then chemical sensing. So the part 3 is more like opening the conversation, opening the discussion. So microfluidics. Microfluidics usually refer to the science and technology of the manipulating and controlling fluid in micro scale. In terms of the volume, typically as small as picoliter, as big as a microliter, sometimes small, little bigger than the microliter. So when we categorize the microfluidics in the big category, we can think about 3 different formats. The first one is a continuous flow microfluidics. Second, droplet microfluidics. Third is a digital microfluidics. Actually, in my lab, we do all 3 different types of the microfluidics because each of them has its own pros and cons. However, today's talk, we're going to focus on the digital microfluidics part because it's the main research topic of my group. At the same time, I just involved with the Sensors Council probably 3-4 years ago. And then as I involved with the Sensors Council, I realized that among the different microfluidic techniques, digital microfluidics is the least represented among this community. So I like to introduce the digital microfluidics in greater detail, and then initiate the discussion among us that how we can combine the sensor technology and the digital microfluidic technology together to have a synergy. Okay, so what's the electrowetting on dielectric digital microfluidics? Let me start from the very basic. So motion by the surface tension control. But, when you are young, you probably have this kind of the fun activities. So this is the plate of the water, and then you have the little piece of the paper as a boat, and then when you drop down the detergent or alcohol works the same, then you can see that the paper boat is pushing, have some kind of proposal. So this actually demonstrates that the surface tension modulation is a very effective way to create a motion in the small object or small scale. Of course, surface tension always exists, but we know that it's not really effective in our scale, the meter scale. You easily break the surface tension. Surface tension doesn't do much things for us. However, in the small scale, because of the surface to volume ratio is much bigger in the small scale, now surface effect is way more efficient and important compared to the body force or body effect. So now, if we can use the surface tension modulation to create the fluid in motion, that's going to be very, very effective way. But using the chemical methodology like this, it's not convenient. It's not reversible, and then every time you have to inject the detergent, it's not really viable method. So we think about, is there any other method such as electrical method? So yes, answer is a yes. And then electrowetting on dielectric is the one possible way of changing the surface tension by applying the electric field, especially electric field between the surface and then the fluid interface. So this phenomena actually starts with electrowetting from the beginning, but in terms of the practical application, electrowetting on dielectric is the one that we are always utilizing. So I'm going to show the example of the electrowetting on dielectric. How it works is that we always have an electrode, and then we have a fluid to operate. Then between these two, electrolyte and electrode, we have the dielectric layer inserted. And then preferably the dielectric layer is a hydrophobic dielectric layer, so that we always have a non-wetting of the fluid on the surface. Now, when we are applying the voltage between these two, the liquid and the electrode, now because of the dielectric, the charge is not transferring, but it's going to be accumulated at the interface as like this. So now the charges are accumulated at the dielectric layer, and then also the counter ions or charges are accumulating the fluid layer as well. This charge accumulation, electric double layer charges is increased, that will result in the surface free energy decrease at the interface. And then because of the surface free energy, which is also known to be surface tension, now the surface tension decrease will create the fluidic motion, because the three surface forces have to be equilibrate, right? So now we make the initial hydrophobic surface to be wetting surface. And then interestingly, because of the dielectric layer can easily charge and discharge discharge. So now when we move the voltage, the charge is discharged quickly, and then now the liquid is go back to the original hydrophobic beading stage. So here, this video shows that applying the voltage, now we can see the droplet is wetting, non-wetting, wetting, wetting. So this motion is now source of the development of the microfluidic device. Now we can do this. Okay, now applying the voltage, we only change the wetting status of the one side of the fluid segment, and then it creates momentarily the pressure imbalance inside of the droplet. Then that will push the liquid in the wetting side. So if we can have a electrode, serial electrode, array of the electrode, and then we can sequentially turn on and off, then you can imagine that we can control the position of the droplet by using the electric signals. So this is a basic idea of the digital. Device architecture is very, very simple. So we just need a substrate, usually glass substrate we prefer, and then the pattern of the electrode, and then we have the dielectric layer coating on top of it. And then we want to have a surface become hydrophobic. So now we have a very thin layer of the usually Teflon. This hydrophobic layer is very important because if your surface is just a dielectric, but it's not a hydrophobic, then your liquid is already wetting the surface. So this the surface center modulation effect is minimized. So we cannot see the effective motion of the fluid. So having a hydrophobic layer is very important. Now this is the bottom plate of our device. And then we need to basically close the circuit of the entire device. So we have a top plate. Top plate is simple. We have a whole layer of the electrode. It can be any electrode, but we want to see through the device when we are doing the experiment. So we prefer having the transparent electrode, which is made out of the indium tin oxide. And then we have another hydrophobic coating. So when we combine bottom and top together, then this is the completion of our device application. So as you can see, device architecture is very simple, easy to make. Okay, so here you'll see the video that how this digital microfluidics is working. We have the transparent electrode. Right now, I think it's a 6x6 checkerboard, the design of the electrode. And then these are the pattern of the different colors of the water. And then by sequentially operating the voltage to the each different electrode, now we can we can create the droplet, which is dispensing of the droplet. And then we can transport, and then we can join different colors. And then we can also split the two, one droplet into two, and then go to the other process. I think the video is not moving over, but you see, now we can do, so using this device, we can create any ratio of the fluid combination, 1:1:1 ratio, 1:2:3 ratio, whatever the composition that you like to create. We can do it because we can operate the droplet individually one by one. So that's why we call this kind of microfluidics as a digital microfluidics, because fluid is handling individually as a one unit droplet. Then you can do all the digital operation and then finish your assay process or your chemical process as you wish. So because of this individually manipulating the droplet, the strong point of the digital microfluidics is we can do the multiplex. So multiplexing means that with the 4 different sources in the beginning, we can create 1,000 different compositions by multiplexing. And then also with configuration means that this is just a mere flat surface. And then we don't really designate the pathway of the fluid. So at the time of use, user can define which pathway the fluid is going. So it's always reconfigure that your wish pathway of the fluid. So this is a reconfigurable, user programmable. These are the strong points of the digital microfluidics. However, one downside of the digital microfluidics is the throughput of this process is quite low compared to the droplet microfluidics. So if you are familiar with the droplet microfluidics through the microchannel, it can create like 1,000 droplets per second, something like that. So throughput is very high. But as you can see, the digital microfluidics throughput is not as much as the droplet microfluidics. So that's the low side. But if your process, especially assay or purification of your sample before the sensing, require a lot of steps and then complicate assay, then this is a solution. Because the droplet microfluidics, high throughput, but the assay process that if you want to do the assay with the droplet microfluidics, it may not be able to do it, or even if we can do it, we need a very careful design of the channel and then the operation schemes. So the digital microfluidics platform can have wide variety of the application possibility. The assay platforms and level of chip and then point of need applications. We can develop a lot of different applications. But as you can see, in order to complete all these applications, microfluidics itself is not enough. It has to be combined with the sensing technology. So we really, this microfluidic people and then also sensor people, we mutually need each other, and then we need to talk more often and more active. Okay, so I'm going to show several examples that we developed in our lab, which is related to the chemical biosensing, possibly. So first example is molecular separation, the purification and isolation. Okay, so especially I'm going to focus on the solid phase extraction, separation, and the liquid extraction. Okay, so sample purification is very critical step for biochemical and environmental sensing. So it removes the unwanted contaminant and interfering substance before it really do the sensing. So by doing this, we can enhance the sensitivity, accuracy, selectivity, and reproducibility of the sensor. And then also it can prevent the sensor fouling and the degradation after use. So here is an example that I have an example of the protein sensing by mass spectrometry. In this case, the salt is the unwanted impurity. Then having the salt actually interfere the mass spectrometry's the signals. So this is an ideal signal like this, but then when you have a certain high concentration of the salt, we showed a lot of noises. So before we are going to the mass spectrometry, we have to clean up the sample and then detect the right protein, the right amount. So in order to do so, the conventional method is using the solid phase extraction, SPE. So SPE working like this. You have to use the pipette tip that packed with a hydrophobic bead. And then now you are getting the sample. And then the hydrophobic surface is attracting the protein on top of it. But the unwanted impurity, which is soluble to the water-based solution, so that the hydrophilic impurity will be pushed through it, but protein is going to be stay in the pipette tip. Now, after then, we can push through the organic solvent. Then finally, we get the concentrated purified sample, and then this sample goes to the detection unit or sensing unit. So then I highlight that electrowetting digital microfluidics always with a hydrophobic surface. So now let me just skip this slide, save the time. Okay, so this is a skin bed. So we have an impurity and sample solution together. We bring it to the surface, the sensing surface. Now we dry everything together. And then now water droplet coming over the dry spot. Then the impurity, which is water soluble, is going to be go to the water. However, the protein, which loves the hydrophobic surface, stay in location. And then now we drive out the water out so that we remove the impurities. And then bring the droplet, the matrix solution here, and then combine together. We are ready to get the mass spectrometry. So here is the result that we intentionally create the different concentration of the protein and then impurity. And then you can see, not rinsed sample is all flat out because of the noise from the impurity. But when we remove the impurity with the methodology that I will show on the digital microfluidics, we can detect the protein, the property. Okay, so now I'm going to show another type of the purification methodology, which is liquid-liquid extraction. Liquid-liquid extraction is known as a solvent extraction. Instead, we have the sample and then solvent together. We mix them together because of the density difference. It's going to eventually settle down in the two different phases again. So oil phase and the water phase. Then among the analyte in your sample solution, some analytes are prefer the oil phase. Some analytes stay in the aqueous phase, so that we can successfully separate the oil philic and then water philic analyte in the two different phases. So now maybe this red molecules are useful analyte, or maybe this blue analytes are useful analyte. We can send it to the sensor. And then so here's the actual example that from the raw blood sample, now extraction can be done by the phenol and then raw blood sample. Now we can separate the RNA, DNA, and then all other the components, protein, and lipids are both dissolving in phase. So now we can collect the DNA and then send the DNA to the sensing unit. So we can do the LLE, liquid extraction, by using the digital microfluidics. Idea is simple. We have the two different phases of the droplet, and then bring them together, and then create the interface, and then let them move around so that create the diffusion process further. And then now among the yellow and green molecules, now green is like the oil phase or the other phase. Then it's going to be diffused into the other phase. Then you're going to completely separate out the two phases. Now we successfully separate the yellow and then green from our cell. Okay, that is the idea. So then I'm going to show our experiment video. So this is the water-based solution. We have the yellow and green dye for our demonstration. And then between the yellow and green, actually green doesn't like the water as much as the yellow. So now green wants to go to the other phase, which is the ionic liquid. Now, as you can see, as we are continuously agitating this two droplets, the green dye is diffusing into the ionic liquid gradually. So when we keep doing it further, you can see that most of the green goes to the ionic liquid. And then now my solution becomes very yellow because we remove the green, right? So after this step is done, we can physically cut off the two different phases. So one phase having a high yellow concentrated, and then the other phase is green. Now we can, if this is the biological sample, now we can send our sample to the sensing unit because it's a purified. Okay, I'm gonna take this next. Okay, so using this idea, we tested the DNA extraction. So usually when we are doing the DNA extraction in the lab scale, we use the test tube and then magnetic field. So this magnetic field idea is kind of the solid phase extraction, but we don't want to use the magnetic field process because it needs a lot of steps. So instead of doing this, we just bring the two different phases, and then now DNA, since this has some charge in there, it actually likes the ionic liquid phase better than the water. So eventually my DNA is going to be moved to the ionic liquid phase, then we can separate the DNA. So right now the extraction efficiency is not that great compared to the commercial kit, but we still have a room to improve this efficiency. So this might be, in the future can replace the common practice of using the magnetic field in the process. Okay, next is the organic chemistry workup, which is now when you are synthesizing the drug component. In the final, the product, it's a mixture of the many different compounds, but you have to really purify the compound to make your final product. So, so at that time, we were developing the drug discovery platform using the digital microfluidics. So we had the organic synthesis done on the chip, and then we needed to separate our product. So a lot of chemistry going on in this slide, but in our drug component, we have the acidic organic acid product and then benzophenol product. Now we have to separate these two compound in the completely separation. So how we do is that we do the neutralization process by adding the base solutions. And then now by doing that, the acid product become the neutral compound, and then it's going to be dissolved into the water phase. But the benzophenol will stay in the organic phase, so we can retrieve this benzophenol. And then later we can regenerate the acid and then finally crystallize the benzoic acid as another compound and another product. So long story short, this is also application of the liquid extraction. So we bring the aqueous solution, basic solution combined together, and then this acid going into the water base, and then the rest of the benzophenol is going to be now crystallized. So we purify it. And then next step, final step, we crystallize the acid separately. So this is a pure benzoic acid. This is a pure the crystal of the benzophenol. So we successfully separate the two chemical compounds, completely mixing the original solution by using the digital microfluidics actuation. So I'm gonna just skip this the data, and then so next example that I'm gonna show is so completely change the gear. So it's not a separation, but we want to create the three-dimensional cell structures, and then using that three-dimensional cell culture structure as the drug screening platform. So idea is when you are culture the cell in the lab, it's mostly in the petri dish and the one layer of the cell sheet. This is not a good replica of our human body. So we rather use the 3D tissue level of the culture so that we can test the drug and then get the more accurate outcome of the drug screen. But when we do it in the microfluidic channel, then 3D means that it's actually kind of gel type. So this gel is going to be completely block the flow pathway, so it cannot really, it's not a viable idea of the 3D cell culture. So our idea at the time was, why don't we use the digital microfluidics and then create the identical array of the 3D cell host or tissue host, and then bring the all different mixture, cocktail of the drug, each of the cell host, and then exact time, exact concentration, exact cell density, everything is identical. So now we can do the apple-to-apple comparison with a different composition of the drug. So that is we use the arginate gel as our hydrogel that makes the 3D cell structure. However, when you are using this typical checkerboard type of the device, we kept failing because in this case, in this application, key is every cell 3D cell structure has to be identical shape, identical volume, identical cell density. Otherwise, it doesn't have any meaning, right? However, when we are using just the checkerboard type of the device, the shape of the 3D culture that we make is all random shape. So now it's not an apple-to-apple comparison anymore. So we have to overcome this problem, and then many generations of the device design, we have to change our mind. Forget about the square shape, forget about the checkerboard. Now we design this ring shape, circular shape, and the ring shape of the electrode. So here the message is that digital microfluidics, although it's a digital, so the checkerboard type of the operation is easy to understand, but we have to stick with that design. The electrode design can be any design based on your application. So now by having this design, we can create the radial symmetry of the all diffusions so that we could successfully create the very identical, nice disc shape of the cell, 3D cell culture. now we put to the drug screening on top of it. So this is the detail of our experiment, but I can skip that detail. And then this is our the demonstrating device. So it's not a high throughput, but we could create the 4 identical the three-dimensional cell structure. And then we can bring the 4 different concentration of the drug candidate here, and then see exact same time, exact same the cell density, everything is the same. Only difference is the drug concentration. And then we could see how many cells died, how many cells are survived after a certain time, so that we can evaluate the drug efficacy using this device. So because of the time issues, I'm not showing this video. This is a very fun video. However, a long video. So I'm gonna just skip and then show the result only. So these are the 4 identical, cancer cell, 3D cancer cell structure that we created using the digital microfluidics. And then now these are the concentration of the drug amulate that we used. And then you can see 0 drug, cancer drug. Now almost all the cells survived. The blue are the light cell, and then this pink are the dead cell. So now we see the more dead cell based on the concentration. So this is a more quantitative data of the cell viability data. And then this is actually time-lapse data because we applied the drug to each of the cell posts simultaneously at the same time. So now we can easily quantify the cell viability based on the time. This shows the time-lapse data. Okay, so next one is organic synthesis, which is eventually for us, we developed it because we want to build the organic, the drug discovery platform out of digital microfluidics. So we tried organic synthesis, but it doesn't necessarily only for the drug discovery the application. It may be useful for the biochemical sensing as well. So the basic question is, so far, we always work with a water-based solution because typically the bio solutions are all water-based, and then we didn't have too much problem to operate those solutions. But what about the organic fluid, like benzene, toluene? Those are very important solvents for the organic synthesis. But when we do the electromechanical model and also experimental validation, our answer for this question is no, we don't have a hope. We cannot move the organic solvent. So, but then we didn't want to give it up. So what we did is another idea, engine and cargo. So engine and cargo means that we're gonna bring some fluid that is movable by the electrowetting. And then now that's gonna be my engine. And then we're gonna get the unmovable organic solvent, that's gonna be our cargo. So we still can do the digital microfluidic motion by using the engine and cargo, and then we can run the organic synthesis using this operation. So long story short, this is actually key thing. So why we are doing this? The thing is, we just have a one simple device, then we can run the 63 by the design of our experiment. We could run the 63 test with a very short time, organic synthesis test. If you do it organic synthesis in the chemistry lab, maybe if you are really lucky, you can finish 2. Otherwise, maybe 1. So it takes about 2 months to finish. 1 person doing it, but we finish it in just a couple of days because the small scale reaction is very fast. And then we can run the simultaneous reaction at the same time by droplet format. So we could run the 63 test with the different conditions, and then we could find out the best solution for this particular reaction. So what's the best the solvent for this reaction? What's the best catalyst concentration for this reaction? What's the outcome of the parallel reaction with a different starting material? All these studies can be done in a very, very short time, and then without the beaker or pipette or anything. So that's the strong point of message of the physics. So also long video. Skip it. These are the detailed results, but I think it doesn't really matter for my message, general message about the proper digital microfluidics. Okay, so I introduced the 3 different examples that we did in the digital microfluidics in the previously. Now this is a main thing for this audience, that how can we use these 2 technologies, the digital microfluidics and then sensing technology together, and then get some synergistic outcome. So I like just to have a conversation and brainstorm. I don't have an answer for this question, but I like to brainstorm with you guys. That's my goal of this talk. So, but nevertheless, I sit down and then thought about it. What can we do? And then I categorize possibly 4 different ways of the fusion of these 2 technologies. So first, the approach is sensors is going to be used to control or operate the digital microfluidics system. What it means is that we need a sensing technology that senses where the my droplet is there. So that it's important for the logistic point, right? Or we have to measure the speed of the drop or shape of the drop. So we need to sensor for that. And then, or this is very important, that if the sensor can find out the device defect, which is surface contamination or some defect of the hydrophobic layer or something like that, then that sensor will be very useful for operation of our device. So I can think about that future. Okay. Second thing is already very actively done, and then several of my examples already did that. Means that EMF is the kind of sample, treatment section unit, and then sensor is the sensing unit, and then possibly we're going to combine that together, and hopefully it's a portable or very small size of the device, so it's going to be useful for the point of care application. So that's the system integration idea. The third one is sensing can be done by the digital microfluidics principle. Okay, I'm going to talk about it later. And then the last thing is possibly sensor is going to be now made or fabricated by the digital microfluidics functionality. So these are the possible fusion that 2 things are getting a synergistic effect. Okay, sensor for digital microfluidics operation. Here are 2 already done research. The first one is measuring the capacitance, so that since the digital microfluidics already have the all electrode pattern on the surface, then we can measure the capacitance between 2 electrodes, so that we can sense where the drop is, right? So that has been already utilized by several other groups. And then here, this is a quite new things. We try to use the image recognition by machine learning, and then use it for the sensing the droplet location, position, and then shape, and so on. And then we want to expand it for even the droplet property sensing. So that is the ongoing research in my research group now. And here, systematic integration, it's been there and it's been done by many other researchers. So here is I found a great cartoon from this recent review paper, and then it showed that these kind of the optical sensings have been used and then combined with the digital microfluidics. Mostly, I think we already use the fluorescence microscope. When you see the cell viability, that's the fluorescence microscopy data. So fluorescence microscopy or the chemiluminescent is the maybe most popular sensing technology that combined with the digital microfluidics. But when you think about the future, I think we have to do more research on the smartphone-based optical sensing, because optical sensing always comes with the special devices, special microscope, special light source, something like that. And then that's not really useful for the point of care point of view. So if we can come up with a really good high resolution, high sensitivity, smartphone basis optical sensor, then that will be really great. Combined together with the digital microfluidics, we can make a handheld type of the whatever the biosensing device can be. So I want this community is working on that area more actively. So, and then in the future synergy will be expected. This is a combination of the digital microfluidics and electrochemical sensors. So like amperometric sensor, voltammetric sensor, and then capacitive sensor, and so on. So this is more straightforward because what we need is just the electrode to sense this bio or chemical component. So there are different ways of integrating the electrode in the digital microfluidics. In this case, the electrode is integrated in the bottom chip of our device. In this case, it is integrated in the top chip. And then this interesting paper is actually integrate the commercial electrochemical sensor to the digital microfluidics, and then they say that, oh, we integrated. So there are, we have to be more creative in terms of the integration. And then I think electrochemical sensor has a much more capability to be the point of care or portable devices. So we need the more collaboration among the digital microfluidics and then electrochemical sensor people to build synergistic systems. And this is the third thing. This is also our ongoing project. Simply, when we think about the electrowetting actuation, how it works is our input signal is electric field, voltage, different amplitude, different frequency. Now we have a fluid as a body, and the fluid has a different properties: surface tension, conductivity, dielectric constant, viscoelastic properties. So based on their property, now it will show the different motions. But we don't care what motion we have because our goal is having some motions as we wish. So this is the actuation part. But now we can flip over our thought process. Then our input still electric signal, but now we create the motion and then detect the motion. By detecting the motion, now we can deduct what's the fluid properties, unknown fluid properties. So right now we are working on this part. This really needs a machine learning part. So we are working on this part to build a sensor for physical fluid property measurement out of the digital mechanisms. And then the last one is sensor built by the DMF function. Some time ago, we wanted to build the digital microfluidics for the blood test, the platform. So at that time, we need the blood metabolic panel capability of our device. So we have to integrate the ion selective sensor, which is detecting the blood sodium concentration, blood calcium, and then potassium concentration. That's important for the metabolic sensing. So we wanted to have it in our device. So then ion selective sensor is very simple. It's a potentiometric sensor, so that we just need a 2 electrode, right? And then on the important part is we need the ion selective membrane, so that now particular ion is selectively diffused into the sensing area, so that we can measure the potential difference between the working electrode and the reference electrode. So then now we can measure the concentration of the particular ion. So we wanted to build this sensor in our device. And there are different ionophores we can buy from the Sigma Aldrich. So we bought the potassium, calcium, and then the sodium ionophore. So this is our sensor, the structure. So this is our device, and then but then the bottom plate of our device has the AgCl, the reference electrode. And then now we have one of the electrode that has an ion selective membrane. But then when the sample solution is coming to the area, now we can measure the voltage difference and then measure the sample solution, I mean the sample concentration. So to build this, however, we have to use the fluidic motion. So the idea is like this. Now we prepare the seed layer of this device, and the device fabrication is done here. So clean room, the MEMS fabrication is done up to the seed layer. Now AgCl, the reference electrode fabrication, and then ion selective membrane, the fabrication is done by digital microfluidic motion. So now later, after seed layer fabricated, we bring the Ag plating solution and then plate the Ag on the seed layer. And then later we bring the HCl solution and then do the oxidation so that we create the AgCl, the reference electrode. And then later we bring the ion selective membrane solution and then create the little portion of the ion selective membrane. And then that's the completion of the sensor plate. This is a video showing that while we are doing the electroplating, you see the silver is getting plated on the seed layer of our device. And then after this, we get rid of this solution by the EMF of the motion. And then next is, now this is how we generate the ion selective membrane on the particular electrode surface. So this is a membrane solution is sitting on the surface, and then we're going to drive this membrane solution by the EMF motion. And then because this opening is a hydrophilic, now we can create the very little volume of the solution right on top of here, pinch of so, right? And then we dry it, and then we create the ion selective membrane. So this actually finish our fabrication of the device using the digital microfluidic motion. And then, long story short, final result is here that we create the array of the sensor. So 3 different sensor arrays are sitting on the same device. And then we bring the same blood sample. Actually, we use the blood emulator sample, and then measure the calcium, potassium, and then sodium ion concentration from the blood emulator simultaneously by using the digital microfluidics motion. So I talk very fast because I have a limited time, but this is the all the things that I prepare. So conclusion is I introduced how the digital microfluidics is working, and then it has the great potential to be applicable to the bio and chemical sensing. But in order to reach there, we need a synergistic effort between the fluidic people and then the sensor people together. So that is my message for today's talk.
Yeah,